Let's focus on the atoms and how atoms are coming together to form complex structures. Atoms, we say that they are made up of a nucleus, right? Containing protons and neutrons, and, and electrons orbiting around the nucleus. Now, as electrons orbit around the nucleus, the area where the electrons are orbiting describes what we call electron shells. These electron shells occur in many numbers based on how many electrons are a part of a given atom, right? Carbon has 6 electrons. These 6 electrons are distributed between the first electron shell here that can house up to 2 electrons and the second electron shell here that can house up to 8 electrons. But because carbon atom only has 6 electrons, obviously we're going to have 2 electrons in the innermost electron shell and 4 electrons in the outermost electron shell, right? How about nitrogen? Nitrogen contains 7 electrons. These electrons, 2 of them are going to be in the innermost electron shell, while 5 of them are going to be in the outermost electron shell. Oxygen has 8 electrons, right? 2 of them in the outermost electron shell, and 6 of them in the outermost electron shell. Okay, we can do the same thing for phosphorus and for sulfur. Now, I have to say that when a given element has enough electrons to fill out both the first and the second electron shell, the second electron shell being able to carry up to 8 electrons, now the extra electrons are going to be in the third electron shell that also can carry up to 8 electrons. Then, based on the atom or the element, you can have a fourth electron shell and so on and so forth. But I'm not going to go into that. When it comes to how atoms come together to form complex structure, we are going to go by what we call the octet rule. The octet rule says that starting with the second electron shell and the third electron shell, every atom that does not have its outermost electron shell completely filled, completely occupied by the number of electrons possible, these atoms will need or will want to interact with other atoms. We say these atoms to be reactive atoms. These reactive atoms are going to react together to form complex structures. However, there are other elements that have their outermost electron shell filled. When they have this outermost electron shell filled, these elements and their atoms are said to be unreactive. This is the case, for instance, for neon, okay, to name only that guy. But carbon, oxygen, nitrogen, phosphorus, sulfur, hydrogen, they all don't have their outermost electron shell filled, so that they are going to have what we call valence shell. A valence shell, it's a shell that needs to be filled. And how is that shell going to fill? Well, that shell is going to fill by simply developing relationship with other atoms. They're going to develop relationship with other atoms by either accepting electrons or sharing electrons, which takes us to another dimension of the chemistry of life, which is the chemical reactions, right? These chemical reactions are going to allow atoms to come together to form molecules. Now, these molecules that are made up of different atoms or similar atoms coming together through chemical bonds form that stable structure. That stable structure can be made up of one single type of element, right? Or that structure can be made up of different types of elements, such as, for instance, water. Water is made up of oxygen and hydrogen. These are two different elements. In that case, the molecule of water is considered a compound. Okay? A compound is a type of molecule that is composed of different elements, right? Now, when we look at how atoms come together, we have some atoms that are going to come together to form a molecule through what we call ionic bond. What is an ionic bond? An ionic bond is a type of bond that forms between two ions. But what is an ion? An ion, it's an atom that has either gained an electron or lost an electron, right? So two possibilities. An atom can gain electrons, in which case it becomes an ion, or that atom can lose an electron, in which case it becomes an ion. But how do we tell the ions apart, whether you are losing an electron or gaining an electron? An atom that gains an electron is going to be overall positively charged. And that overall positively charged atom is now called ion, and that ion is called an anion. An ion. All right? Because it is negatively charged, right? By the same token, an atom that has lost an electron is now going to be overall charged positively. This is not an atom anymore, it's an ion. That ion, it's called cation. Cation is positively charged, anion is negatively charged. Now, some elements, when considering their outermost electron shell, rather give up their electron or accept an electron from another atom. Now they are going to come together through being two ions, charged differently, one positively charged, one negatively charged. That's exactly what happens between sodium and chlorine, right? So that we have a sodium ion here and a chloride ion here. And these two are stabilized by negative and positive charges attracting to each other so that they form a crystal. That crystal is very typical of salts, right? So the salts are the one that are going to form based on ionic bonds, right? Sodium chloride, which is the table salt, right? It's very much a molecule that is formed based on ionic bonds. Now, that's the first type of bond that we're going to address here. The second type of bond that we're going to address is going to be the covalent bond. The covalent bond, it's a type of bond where atoms are going to fill their outermost electron shell by simply sharing electrons, right? So here I hydrogen and another hydrogen, right? They are going to share their electrons so that they each have a maximum electrons in their outermost electron shell, so that we have hydrogen gas here. How about oxygen? Oxygen gas, it's one oxygen atom and another oxygen atom, right? They are sharing their electrons here to actually fill out the outermost electron shell. That's another covalent bond here, there. Now I have to say that covalent bonds are much more stable, much more strong compared to ionic bonds that are easy to break, particularly in presence of water. But how is it possible that water is readily breaking salts compared to covalent bond? That's another story that we are going to address in a minute. Before we address that story, let us dive into the chemical reactions. Looking at the chemical reactions, two different chemicals are going to come together to form something, right? The two chemicals that come together are called reactants, okay? These reactants that come together, in the case of photosynthesis, here we have carbon dioxide that combines with water to produce a molecule of glucose. Glucose is going to be the product. Oxygen is the gas that is also produced as a byproduct of photosynthesis, right? So in a chemical reaction, you are going to have reactants that are always on the left side of the equation and products that are always going to be on the right side of the equation, right? Please remember that. Now, the molecule that forms out of that chemical reaction, we are going to write it in a certain way. For instance, in the case of glucose, we have C6H12O6. Now, each number represents the number of atoms of that element, right? So you have carbon, the element of carbon is represented 6 times in a molecule of sugar. The atom of hydrogen is represented 12 times, while the element oxygen is represented 6 times in this molecule of glucose, right? So the proportion of each of the element in the structure of the molecule is very important, right? Now, let's switch our gears to water. Water is essential for life. Let me repeat that. Water is essential for life. But water is not a molecule of life. Again, water is essential for life, but water is not a molecule of life, because we do have some molecules that are molecules designed by living systems. We call these molecules molecules of life, right? We are going to address these molecules in the second part of this lecture presentation. Now, water is very characteristic But let's dive first of all in the structure of water. Water is oxygen to which two hydrogen atoms are attached, right? We can ask, okay, well, how are they attached? They are attached via covalent bond. Now, with that being said, we notice that in a molecule of water, as oxygen and hydrogen share electrons, that sharing is not equal. Okay? Electrons tend to spend more time closer to oxygen than they do to hydrogen. This is causing that molecule to behave not like traditional covalent bonds. Rather, they are behaving as if one side of the molecule, the oxygen side, was slightly negatively charged, while the other side, the hydrogen side, is slightly positively charged. Now, these slight charges obviously are not absolute charges, meaning that if you look for these charges, you're not going to find them, right? However, they provide to water a certain property. That property of water, it's that water is going to be a molecule that is a polar molecule. This polar molecule is caused by the covalent bond, so that water molecules are considered polar covalent bond. The covalent bond in water molecules are considered polar covalent bonds. Now, this is happening because when we look at the capability of these two elements to attract toward themselves electron, we notice that oxygen has a very high electronegativity compared to hydrogen. Because of that, electrons in the sharing of electron between oxygen and hydrogen are spending more time close to oxygen than they do close to hydrogen. Because of that, when we put several molecules of water in a bucket, these water molecules are going to behave like magnets, so that the negative poles are going to attract the positive poles and vice versa. So that in a water-based environment, like a body of water, we're going to have some connections that are going to develop. These connections are strong attractions that develop between the slightly negatively charged area of oxygen and the slightly positively charged area of hydrogen. And the chemical bond that forms as consequence of that is called hydrogen bond. This hydrogen bond are the reason why you have drops of water that form. Okay? When you have many molecules of water that are on a surface, these molecules of water tend to stick together. They tend to cling together, right? Now, because of that property of water molecule clinging together, and also because some molecules out in the environment are what we call salt, right? Including sodium chloride. Well, salts are made up of two ions or more, right? Connected together. In presence of a polar molecule such as water, This salts become very easily soluble in the presence of water, so that water is a solvent. Actually, we call water to be the solvent of life. Why do we call water to be the solvent of life? Because, believe it or not, water makes up a huge amount of your body, right? About 70% of your body account for water, which means that everything about you is dissolved in water, right? So that when we consider water to be the solvent of life, we are going to actually classify chemicals that are in presence of water in two categories. The chemicals that are going to attract water or be water friendly, these are the hydrophilic compounds or hydrophilic molecules, and the chemicals that do not like water. They're going to repel water, stay away from water as much as possible. These are hydrophobic. So hydrophilic are water-loving molecules. Hydrophobic are water-hating molecules, right? So now, when we consider water in living systems, I already told you that regardless of the living system, water molecules cling together, right? Between molecules of water, you have a property that we call cohesion. That cohesion is what allows molecules of water to come together. By the way, for the sake of the exam, I always ask this following question. Within a molecule of water, what kind of chemical bonds are you finding? Let me repeat that. Within a molecule of water, what type of chemical bonds are you finding? I'll let you think a minute about that. The second question, similar to the first one, between molecules of water, what kind of chemical bonds are you finding? Okay? Between molecules of water, what kind of chemical bonds develop? I'll let you think about that. Okay? So, and I challenge you to find an answer to these two questions. Now, cohesion, again, it's water molecules attracting each other, right? As they attract each other, they are going to work toward a forward flow. But let me close that parenthesis. Water also interact with structures around them, right? When they interact with structures around them, the type of bond that develop between the structures around them, it can be other chemicals, it can be walls, and so on and so forth. The type of connections that develop are called adhesion, right? Are called adhesion bonds, okay? So I want you to remember cohesion and adhesion. Now, cohesion is the reason why a tree, such as an oak tree, can suck water from the ground and pull that water all the way up until you have an evaporation of water from the tree, right? Water in the ground is in the form of liquid. Evaporation, it's water in the form of gas, right? So whenever a water molecule is leaving, it is pulling another water molecule that is in the form of liquid, okay? And how is that possible? Because of the polar property of the molecule of water, right? It's a polar covalent bond. So they react like magnets, right? So remember adhesion property, remember cohesion property. The next aspect of water that I'm going to address is the fact that because water molecule stick so much together, some organisms can literally walk on water. Okay, because some organisms have something underneath of their feet or on their body that is water repellent, right? They are going to not be able to sink in the water, right? Because now we have a property which is surface tension of water, right? So here we have these striders, these water striders that are literally able to walk on water because the water molecules are sticking together, while underneath of the feet of these insects, you have water repellent molecules. And these water repellent molecules are the one that allow this insect to literally walk on the water. Okay, water does not only have a high surface tension, but also water is a temperature buffer, meaning that water resists a change in temperature. It takes a lot of energy to boil water, okay, to change the temperature of water. But water, when we exercise, when it's hot in the environment, can also break the diffusion, the radiation of temperature inside of our body. So when it's hot outside, our body feels the heat, we start sweating, and that small film of water is enough to break the radiation of the heat inside, right? That speaks to how water is a temperature buffer. Now, this slide actually gives you a summary of the properties of water. Water is a solvent. Water is cohesive, adhesive. Water has a high surface tension. Water can evaporate, right? It resists actually change in the temperature, right? But water also has a different density, whether it is liquid, solid, or vapor, right? Ice cubes are going to form some rigid structures. As you see here, these rigid structures cause molecules of water that are clinging to each other to be as far as part of each other as possible, so that in the ice, the water molecules are going to be far away from each other. The same quantity of matter in a liquid form is going to occupy less volume. Because of that, ice is going to be less dense than liquid water, causing actually ice cubes to float in water, right? Now, water molecules can split. When they split, actually, they're going to release two chemicals, hydrogen ions and hydroxide ions. Okay? Now, because when water splits, it can release hydrogen ions and hydroxide ion, we can always ask the following. In a water-based environment, do we have more hydrogen ions than hydroxide ion? Or do we have the same quantity? What is the concentration of each of these ions in a water-based environment? Now, When I say water-based environment, that means that water is hardly by itself, right? It's very difficult to find pure water, right? Now, obviously, pure water would have as much hydrogen ions as hydroxide ion, okay? This would be in an ideal solution of water, which is pure water, right? But we know that in nature, things do not work like that. So we are going to ask the following. Well, the chemicals that come in contact with water, how do they behave? Well, we're going to classify them based on the following property. Well, when the molecule splits, does it release hydrogen ions or taking up hydroxide ion? That's the first scenario. The second scenario, is it taking up hydrogen ion or releasing hydroxide ion? In both cases, we are going to name this chemical substance based on that definition. Whatever substance is releasing hydrogen ions or taking up hydroxide ion is considered an acid substance. By the same token, a substance that is taking up hydrogen ion or releasing hydroxide ion is considered a basic substance. It's a base, right? So we have some chemicals that are acids, others are bases. Acids are going to release hydrogen ions, while bases are going to take up hydrogen ion, okay? Now, then we have other substances. These substances actually are able to resist change in the concentration of hydrogen ions and hydroxide ion. Whenever they are able to resist that change, we're going to call the substance to be buffers. Now, you have that buffers are able to resist pH change, but what do we call pH? P stands for potential, H for hydrogen. Because the molecule of water is able to split into hydrogen ion and hydroxide ion, each of the ion is going to be concentrated. So we are going to ask the following question: what is the concentration of hydrogen ion and what is the concentration of hydroxide ion, right? Now, because it is not always convenient to navigate between the concentration of hydrogen ion and that of hydroxide ion, we've come to an agreement that we are going to focus on the concentration of hydrogen. So we are going to ask the following question. In a water-based environment, what is potentially the concentration of hydrogen ions? That's why we are going to call, to say potential hydrogen or pH, right? What is potentially the concentration of hydrogen ion? With that being said, buffers are going to resist pH change. And the blood has a pH that varies between 7.35 and 7.45, 7.4 being the average. That average is going to be maintained by buffers in our system, right? When this is not possible, that can lead us to being in a health condition that can be difficult, right? One such condition is acidosis. Acidosis is when our internal pH is acidic. We have more hydrogen ions than we do have hydroxide ion, right? When that happens, this can cause conditions such as congestive heart failure, right? Or diabetes, which both conditions could lead to death, right? So this can be relatively nasty. Now here, I'm showing you a pH scale. That pH scale varies from 0 being extremely acidic with high concentration of hydrogen ions to 14, meaning very basic, high concentrations of hydroxide ion and low concentration of hydrogen ion. So anytime you have a high concentration of hydroxide ion, you're going to have a low concentration of hydrogen ion. By the same token, whenever you have a high concentration of hydrogen ion, you're going to have a very low concentration of hydroxide ion. They are complementary, okay? So that only pure water has as much hydrogen ion as hydroxide ion. That pure water has a pH that is equal to 7. That's a neutral pH. Only pure water can achieve that. Anything else goes above or below that pH, okay? Because you either have a, a high concentration of hydrogen ion or a low concentration of hydrogen ion, right? So here you have some examples of substances that are acidic, including the stomach juice, right? Lemon juice, Coca-Cola, beer, vinegar, tomato juice. They are all acidic. Black coffee, while other substances are basic, including seawater, the human blood, baking soda, the Great Salt Lake, okay, milk of magnesia, are all basic substances, okay? So this actually is going to close the first segment of this chapter that focused on the basics of the chemistry of life.